like example one, I like example one, I like example one. Example one is a nice question. I like it for a couple of reasons. First of all, I played with slingshots when I was a kid. One of my early memories, whenever we went camping as a family, the first day my dad would take his 3 sons into the woods and he would carve us all slingshots from various tree branches. We would dry them out in front of the fire, make sure the wood was nice and dry, and then the next day he would carefully lace the rubber on, and all of us would have slingshots to play with for the rest of our trip. We put good mileage on them. But also there's great physics in slingshots. A slingshot is pulled with an average force of 70 newtons for a distance of 90 centimeters. Okay. Hannah, what's A want me to find? You're with me now, Hannah?
No.
Stay with me, please. Thank you. What's A wanting me to find? Now, here's the most common mistake that drives me cuckoo for Cocoa Puffs. Look up. Don't write this down. I see kids go, oh, potential energy is mg. Don't write that down. Look at the picture. Are we lifting this object to a higher height? Is it gaining gravitational potential energy? No. In fact, for a slingshot or a bow and arrow, the potential energy is being done by work. Force times distance. Hannah, what's the force? Good. What's the distance? Don't say 90. Nice try, Dewick. 0.9 meters, right? Okay. How many joules of energy are stored? And because it's stored, that's why we're calling it potential. Not gravitational potential, just potential. How many joules of energy are stored in this slingshot? Raphael, what'd you get? Oh, he's going to get his calculator out now. Look at him. Excellent. Is it 63? Should be, yes? Okay. When we let go of the slingshot, what does all that stored potential energy get transformed into? Kinetic. Okay? So part B says, how fast will it leave the slingshot? First thing I'm going to say is, all of that potential gets turned into what? Now, if you want to, this is actually the law of conservation of energy. Here's what we really said. Don't write this down, but look up. We said, okay, potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Starting at rest, so no initial kinetic energy. And after it leaves the slingshot, it's used up all of its potential energy. Or you could go straight to saying all of the potential is turned into kinetic. You see, you get the same thing? What was the potential? Not mgh, it was 63. Kinetic is a half mv squared, but I'm going to write it as mv squared over 2. Kayla, what do you want me to find in part B? Yeah, I'm going to get the v by itself. Where's Mr. Dewick being a bit sneaky? Of course, I'm sure, Kayla, you saw that 35 grams and said, nice try, Dewick. I'm not going to go work for Verizon. 35 grams, how many kilograms is that? 0.35? I think I disagree. 0.0, remember, it's out of 1,000. 0.035 kilograms. Okay. Kayla, how would I get the v by itself? What will I do with the m? Yep. What will I do with the 2? Squared? So you're telling me it's going to be 2 times the 63. You said times the 2. Yes, you're right. And then divide by the m, which was 0.033. 3, Mr. Dewick. 3, 5. And what did you say we had to do? Square root. No slingshots going 4,000 either, right? What do you get? This might work out nice. Does it? Oh, it doesn't? Okay. I thought maybe it did. I was seeing a 7 cancel and a 9 left behind. Oh, yeah, okay. 2 times 63 divided by 0.035. Yeah, it works out nice. Telling me it does. 60 even, yes? Yeah. Probably. Is that a hand up, Mesa, or are you just poking your head? We did use the half mv squared. So like make the 1/2 a 0.5? So then what you would do is instead of timesing by 2, you would divide by 0.5. Okay? So you would have this. 63 divided by, you would have two things on the bottom, 0.5 times 0.035, and then square root of that. Do you want me to write that out? I'll show you. Over here where I have some space, you would say, okay, 63 equals 0.5 mv squared. I would divide by 0.5 m to get the v squared by itself. And then how do I get rid of a squared? So help me next year, you're sitting further up at the front. Like that. That'll work. By the way, the reason I don't do that in math, it's sloppy manners to have a decimal inside of a fraction if you can avoid it. It's like you have commitment issues. Pick fractions or decimals, but don't waver. Tarzan weighs, oh, sorry, I forgot to write the answer. 60 meters per second. That seems ballpark about right. 60 meters per second, that's about half a football field in a second. That's how fast, like I could follow the rock with my eyes. It was going faster than I could throw, but it wasn't going like bullet speed. Okay. Tarzan weighs 82 kilograms and can run at 8 meters per second. He runs along the ground and grabs a vine swinging into the air. What maximum height does he reach? Rope swings are great examples of conservation of energy. What does DOLP mean? Draw a little picture. We're going to DOLP. We're going to draw a little picture. So here's Tarzan. Let's have him running. There's my stick figure Tarzan. Here's the rope swing he's going to grab. And he's going to swing up. And I guess it wants us to find the height. Is that all right? Is there a change in height when he grabs the rope swing? In other words, when he grabs the rope swing, will he swing up? Will there be a change in speed when he grabs the rope swing? Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? Probably conservation of energy is our best bet. So let's go like this. KE initial plus PE initial equals KE final plus PE final. Are any of these zeros? Let's see. Potential energy, if we're talking gravitational potential energy, that'll be 0 if we're on the ground. Are we ever on the ground? I think at the beginning, right? PEI, not a real problem. Is potential energy final 0? No, in fact, I think the H that I'm looking for is hidden in there. Yeah. Quinn's looking skeptical. You good? What about kinetic energy? Kinetic energy is 0 and we are at rest. Are we at rest right here? Where are we at rest? At the top for a split second, I think, right? I'm imagining how a rope swing works. We're going to swing up and come to a stop. So I think I can say that. So this really, really complicated question with curves and change in heights and change in speeds and rope swings actually ends up turning into a half mv V initial squared equals mgh final. Oh! Huh. I noticed something. Is there an m in everything? So what happens to the m's? What does that mean? Well, that means that if Tarzan runs at 8 meters per second, and if Tantor the elephant runs at 8 meters per second, assuming the rope doesn't break, Tantor the elephant and Tarzan will swing to the same height. If the vine breaks, that's a different story, but let's pretend it's a vine that's not going to break. Doesn't matter. If you're running at 8 meters per second, you'll all get to about the same height. What are we trying to find? Height? Odetta, how would I get the h by itself? How will I move the g over? Yep. H final is going to be V initial squared. Mesa, you could put a 0.5 in front of the V. I'm going to put a 2 here next to the G, and I'm not going to bother writing the 1 because the 1's not going to make a difference at all, but it's still a half mv squared. It's going to be 8 squared all over 2 times 9.8. Y'all get 3.27? Meters. Is there a good rope swing in Pitt Meadows on Pitt Lake that people know about? I grew up in Abbotsford, so I know there's one out in Hope, and I know there's one out on Cultus, but I don't know if there's one out on Pitt Lake. There is? People are not? Okay. So rope swings are good. I know the Abbotsford pool actually had a rope swing that they had set up, so you could take a run, grab it, and swing out over the pool, and that was a lot of fun too. Good physics in rope swings, as long as you're doing them safely. Slap shots are great examples of energy transformations. I'll get to the video at the end of the lesson, but let's keep going because I think we just have a couple more roller coasters and some thought puzzles, and we're done. Roller coaster below has a mass of 255 kilograms. If the coaster just barely makes it over the first hill at location A, how fast will it be going at B? So let's put a little I by location A, a little final F by location B. And if we just barely make it over, I think what it's saying is assume that VI is 0. How am I going to solve this? How am I going to solve this? Is there a change in height? Is there a change in speed? Is there a yucky curvy path? Conservation of energy. Absolutely, Lee. So I'll start out by going KE initial plus PE initial equals KE final plus PE final. I think on your sheet I put PE in front of KE. As long as it's initial plus initial equals final plus final, you're fine. I'm just going from memory. Eliana, are any of these 0? Ooh, what's VI? So what's KEI? I turned the speaker off before I coughed. That was good, because otherwise Mesa would have really jumped. So we can do that, yes? Oh, and we can do that, yes? So I kind of like these roller coaster questions because they start out looking really complicated and tricky, but it turns out you get something kind of elegant, fairly simple. It's going to be mgh initial equals a half mv final squared. Eliana, are you a roller coaster fan? Me too. Have you gone on roller coasters before? Before you got on, did they make you stand on a scale? Did they have to spread people out? Did they have to make sure that all the seats were filled? Why not? Well, that's kind of cool. As far as I'm concerned, I can either give you the initial height and say find the speed at the bottom, or I can give you the speed at the bottom, find the initial height of the first hill. Either of those are fair game. Here, we're being asked to find the speed at the bottom. Mesa, I'm going to times by 2, but you could divide by 0.5, but I'm going to times by 2. So I'm going to get this. VF squared equals 2GH initial. How to get rid of a squared? Square root. It's going to be the square root of 2 times 18. No, times 9.8 times 18. What do you get? Sorry? I don't know what you got. I know the answer is going to be bigger than 0. 18.8. Anybody else? Yeah. Round it off properly. Uh, 18.8 times 3.6 is how many kilometers per hour? Half hour line, maybe. Hour line, I'm going to go get lunch. Hey, let's suppose instead the roller coaster had an initial speed of 22 meters per second at location A. Same approach, it's still going to be KE initial plus PE initial equals KE final plus PE final. But this time, only potential final is going to cancel. We do end up on the ground, but Kayla, we're not starting at rest or ending at rest. It's going to be a half mv initial squared plus mgh initial equals a half mv final squared. Wolf, are you a roller coaster fan? Yeah? You've been on them before? Before you went on the roller coaster, did they make you stand on a scale? Did they spread everybody out to make... Why not? Thank you. I thought you were going to blow the punchline for a second there. What are we trying to get by itself? The V. Now, you could, Mesa, divide by 0.5, square root. But I prefer to go times by 2, times by 2, times by 2. I'm allowed to do that. I multiplied everything by 2. Equation solving says as long as you do it to everything, you're okay. And the reason I do that is here, that 2 and that 1/2 cancel. Here, that 2 and that 1/2 cancel. And I get my old October friend, VI squared plus 2GH initial. You know what? That's VI squared plus 2AD in disguise. That equals VF squared. So I do that as kind of a built-in, hey, error check. That looks familiar. I probably got this set up right. And then how to get rid of a squared, Wolf? Okay. Now how fast am I going? If I come over the hill at A at 22 meters per second, plus 2 times 9.8 times 18, square root of all that, I think I just made it a better coaster. Oh, no squared, Mr. Dewick. Square root. A little better. 28.9, yes. Times by 3.6. Yeah, over 100 kilometers an hour. I'm in. Turn the page. Suppose the roller coaster in part B is only traveling at 25 meters per second at the bottom, not 28.9. How much energy was lost to heat? Ooh. Kyle, what does this want me to find? How much energy lost to heat? How much what? This is a job for conservation of energy. G. It's going to look like this. KE initial plus PE initial equals KE final plus PE final plus, this time they want us to include heat, so we tack it on the end. We can still say that potential energy final is 0 because we are ending up on the ground, Dean. But we're not starting at rest or ending at rest or starting on the ground, so nothing else is 0. Kyle, how would I get the heat by itself? Yeah. Heat is going to be, so the KE initial will drop down like a domino, the PE initial will drop down like a domino, but we're going to minus the KE final. And now we'll expand this and plug and chug. Heat is going to be a half m V initial squared plus m G H initial minus a half m V final squared. Kyle, do the m's cancel this time? Fine. Heat is going to be 0.5. What was m, Mr. Dewick? 255. And V initial 22, because we're doing part B, plus 255 times 9.8 times 18 minus 0.5 times 255 times, we're only doing 25 at the bottom. Don't forget the squared. What do you get? I think you're going to get something in the thousands, I think in the tens of thousands, actually, like 20 something. I'm going from rough guess, but I could be off. What'd you get? 27,400 and... So just above 27,000? Is that right? Anybody else? I'll just go 27,000 joules. No? Yeah? Did I get confirmation? Yeah? Okay. We're going to skip example 4. It's another roller coaster, but we did one already. And I've talked a bit about Rube Goldberg machines. I'll talk about that a bit more. But a bouncing ball, example 5, is a great example of the law of conservation of energy. So if you take a basketball, let me pause the video for a second. At the top of the bounce, what type of energy does the basketball have? Can you write down PE for part A? Technically gravitational potential, MGH, right? Okay. What about at the bottom of the bounce? So here's the question, KE, kinetic. I noticed that if I just let it bounce, it doesn't bounce as high as when it started. Doesn't that violate the law of conservation of energy? If energy is conserved, shouldn't it bounce back as high as it started? Where's it losing energy to? Sound, you heard. Also, actually, a fair bit of heat. Any basketball players here? Yeah, you might recall the Saturday morning game when someone takes the basketballs out of the coach's trunk. The basketballs are flat. You pound them really hard against the gym floor. You're actually sending heat into the basketball to try and warm up the air to increase the pressure and get a better basketball. So our answers for part A is PE, right? For B, KE, no, we are losing energy to sound and heat. So here's the thought puzzle. Is it possible for a ball to bounce higher than it was originally dropped? If I take a ball, and I hold it out, and I drop it, is it possible for the ball to bounce higher than I originally let it go? Someone said yes, someone said no. Convince me. Yeah. Yes or no?
Yeah. If you throw hard enough, then it might go past the plate.
I'm not throwing. It says drop. Right? I very specifically used the word drop. I'm going to hold it out. And I'm going to drop it. Can it go higher than I let it go? So, if a golfer wants to hit their drives further by increasing the kinetic energy of the golf club when it strikes the ball, what would have a better effect? Doubling the mass of the club head or doubling the speed of the club head, and why? Why speed? You're right. What's the equation for kinetic energy? Yeah, go ahead. Look at your sheet. You don't have to memorize these if you don't want to. Right? Memorize them if you're lazy, but what is it? Half mv what?
Squared.
V what?
Squared.
There's the difference, the squared. If I double the mass, I'll get twice the kinetic energy, roughly twice the distance. If I double the speed, because of that squared, what's 2 squared? What's 2 squared? I'll get 4 times the distance. Okay. Assuming that we're in our perfect physics world, we're not losing anything to air resistance and all that. You'll get roughly 4 times the distance, 4 times the energy. And this is why I told you sports equipment over the last 20 years has become lighter, not heavier. What's your homework? Number 1 is good. Skip 2, 3 is good. Four is good. Skipping 5, 6, and 7. 8 is okay. You know, I'm not wild about a lot of these. I clearly need to redo this assignment. I'm going to do 12. So 12. 14 I like. And we're done the unit. On Monday,